we just saw how to use Fourier tail bounds to construct fractional PRGs. And I want to also mention that you can use random restriction lemmas if you can prove that the family of functions that you want to fool somehow simplifies under a p-random restriction. Then you can use this itself in order to construct a fractional PRG. And in fact, I don't have any applications for this to give, but I think it's an interesting thing to know if you want to, if at any time you wanted to come up with a pseudorandom generator and you felt like it's easy to show that your family simplifies under a truly random restriction. So what's a p-random restriction? It's just a random variable over, oh, whoops, that's no good. Yeah, so it's a random variable that takes -1, 1 star to the n values, and we think of the stars as the the variables that we leave alive, and the ones and -1s are the restricted variables, and we leave a variable alive with probability p, and it's a uniform bit otherwise. And a generic random restriction lemma or a switching lemma type statement will say that all the functions in this family that I care about simplify with high probability under random restriction. And for the purposes of pseudorandom generators, you should think of simplify as in we can fool them easily. So for example, their degree drops, or somehow their L1 Fourier bounds drop, that we can use basic generators to fool this restricted function. And this is a general method to construct pseudorandom generators, which is to de-randomize this statement, try to de-randomize this statement and come up with a pseudorandom restriction lemma. And this is essentially this Itai-Wigderson framework, but all of the applications that we know of are not very generic. The de-randomization itself looks into the proof of the restriction lemma for the family and tries to show that the same proof will go through using pseudorandom restriction by using further properties from the family. And what I will show is that you don't need to necessarily do this unless, if you are willing to lose a little bit in these parameters, if you're willing to pay for this reduction from FPRG to PRGs that we had. And the trick is kind of simple. So let's just formalize what we mean by this random restriction lemma. So let's say that we actually have a generator that fools the restricted function with high probability over the restriction, and this is a p-random restriction. And it will be helpful to think of the restriction as just a pair. One is a set, which is a subset of the variables where we pick each of the variables with probability p. So these are the alive variables. And we have a uniform distribution over the restricted variables outside of A. Okay. And we will make the following definition. So we will define f sub p of x to be the expected, so this here we have f, the restricted function that the restriction gives us. So the restricted function on input x will plug in the x values on the alive indices, and it will plug in the uniform outside. So we will define this f sub p to be just the expectation of all of these restrictions of f. Right? So this is some real valued function. Why do we do this? It's because it has the following nice properties. So first of all, if I take the expected value, so if I look at f of 0, which is the expectation of f, it's basically the same as taking this and taking its expectation over the uniform distribution when x is uniform, right? Because it doesn't matter what the set A is if I'm plugging in uniform here. I have uniform in A and uniform in A complement, so I just get the expectation. So f of 0 is equal to this quantity where I'm now, it's close to this quantity. Why? Where instead of uniform, I'm plugging in this G. Why is that? Because this f is a restriction of the original function, and I know that with high probability over a and u, g fools this restriction. So I can replace the uniform with g sub a. So these two expectations are close to each other by the restriction lemma. Right? So I'm being sloppy. I'm just talking about high probability, etc. But let's do that. And the next thing is you can actually look at this expectation here. So the input, in fact, is a random vector, and it has a product distribution. Each of its coordinates is either xi or a uniform distribution, and it's going to be equal to xi with probability p. So this function is nothing but f evaluated at p times x by multilinearity. Right? Does that make sense? So this function that we defined is just some expectation over this random vector, which each of its coordinates is an expectation p times xi. So fp of x is just f of px. Now, combining the two, we are done. So what we have shown is that f of 0, which is this guy, is close to this quantity, which is really, by this definition, it's f of p times g, right? So this x is just the g. I'm plugging in g for this equation. So what we have shown is that f of 0 is close to expectation over g of f of p times g. So what this says is that p times g is a fractional PRG for the family f.
So here, one question, please. See here, assuming that g fools f rho without knowing rho, right?
Exactly, without knowing. I mean, with high probability over rho, g fools rho, f sub rho.
Okay.
Does that make sense?
Mm-hmm.
Yeah.
Well, in some sense, you're using even something weaker. You're using the fact that your generator fools the average of random
expectation. Exactly. So, and this is something that's already used in some applications of this Itai-Wigderson method also, right? So sometimes it helps to fool the expected restriction instead of just showing that with high probability we can fool the restriction function. And here we could ideally use that to our advantage in our random restriction lemma. So maybe we can fool this expected function easier, but yes, so you could formalize it in different ways. But I think the general thing that's interesting is that we didn't need to look at the family F. So as long as you can show a truly random restriction simplifies the family, then you get some PRG out of it.
I guess
and you can see that this P times G.
I was just pointing out that like in some sense, G is still on n bits, right?
Yes, G is on n bits.
Like, usually when we apply Itai-Wigderson framework, you get to design something only on P times n bits.
It's true, but most of the constructions, we say that like k-wise independence fools it, so you can do k-wise over n bits instead of the pn bits. But I see your point. Yes, so we are treating it as a function over n bits right now.
Like in one of our papers, when we used shrinkage to build PRGs, we were using extractors, so you needed to know the order and do some other stuff.
Exactly. And in fact, you can't use what I just said for getting any PRGs in that framework in the first place. Like as soon as P is not very small, we don't get anything, P is not very large then we don't get very interesting things, because if you remember the reduction from FPRGs to PRGs, we'll have this 1 over P squared in the seed length, which kills us in a lot of applications. If your random restriction is very aggressive, then it just doesn't give us anything interesting.
So it seems that it's still open whether we, like the Itai-Wigderson, for example, framework like when we work hard and prove all these things, then we usually get the 1/p dependence.
Exactly. So we have a square loss here as opposed to the Itay-Wigderson. So the loss in the seed length of applying repeated pseudorandom restrictions is usually just roughly 1/p, as opposed to here, we are taking this random walk that needs 1/p squared steps. And that's because this is p squared noticeable, this fractional PRG. That's a very good point, Abhishek. So there is a gap. If you can de-randomize the restriction lemma, you should do that first. If you can't, then you can hope that maybe this p squared is okay.
But is there hopes that maybe there's a generic way? Because so that's maybe was my point, that you're relying on a weaker assumption on the class that you fool the average. If you maybe know that you can fool a random restriction, maybe this stronger assumption, maybe I don't see how to use it, but it could be potential that if you know how to do that, then you could potentially get the 1/p dependence.
Oh, that's there's a. Oh, I think Shachar has a point that there is a 1/p squared lower bound because all Boolean functions have L1AB bound for 1/square root. Yes, that's actually a good point. So Shachar is pointing out that there is a lower bound on this random walk, which is 1/p squared, because all Boolean functions satisfy L1AB with the square root n.
Yeah,
it's a good point. But maybe there is there is some other way of doing this.
So if you imagine like applying the random restriction, you can also think of it as it's like a degenerated fractional PRG, where at each step, some of the coordinates are 0 and some are become either 1 or -1. All right, so that's obviously you need too much randomness in order to implement it. So, but
right,
yeah,
and there's also this question of what if you don't go all the way with this random walk? So maybe you can stop it early and show that now this family simplifies enough that you can fool it in some other ways. So there's questions that you can ask about. So how can you do a hybrid between the random walk and other ideas, which I'm not sure what the answers are. So good questions. Okay. And so let me discuss some further directions and some more recent developments on this area. So what we showed is that if you have a bound of b to the k on all the kth level Fourier coefficients of L1 bound on the Fourier coefficients of the family, then you can get a PRG that has seed length roughly 1/b squared polylog n over epsilon. And L1k here is just the sum of the absolute values of the kth level coefficient. So in particular, for any family that you have b that's polylog n, you get a polylog n seed length PRG out of this. And the question is, well, can we use this to get PRGs for interesting families like degree d F2 polynomials, where d becomes where we reach the barrier for the current state of the art. So we know Viola's generator has seed length d times 2 to the d. That's the state of the art, and this completely trivializes when d is equal to log n. So can we hope to use this to get something better? And at least we conjecture that for F2 polynomials, you have some L1 bound that's exponential, where b is just exponential in d, and this would at least give us some matching generator for Viola's generator, so in terms of seed length. And so what we can prove for F2 polynomials is that the kth level L1 Fourier coefficients, L1 norm of the Fourier coefficients is bounded by a quantity that's like k times 2 to the 3d to the k. And you can see that this is problematic for our application because this K is growing. So you don't have like just this one B that's bounded for all of the levels. But we do manage in another work to bound the first level by something reasonable. It's O of D. So this is our current understanding of the Fourier coefficients of F2 polynomials. And it is an interesting question to try to improve this, this bound. And one way to try to improve on this work is to say, well, we couldn't prove very good bounds for all levels of F2 polynomials, but what if we could prove it for only some levels? And can we use this to construct a pseudorandom generator? So is it necessary that we need this bound on all the levels? And we did study this question in a joint work with Eshan, Shachar, and Avishai, where we showed that only the second level is already sufficient. So having a bound on only this n choose 2 Fourier coefficients at the second level, showing that they sum up to at most some quantity t, we can construct a pseudorandom generator out of this that has seed length polynomial in t and log n. And I'm hiding the dependence on epsilon because it's not good. It's polynomial, it's not logarithmic in epsilon. And the idea here is, so we build on this work of Ranraz and Avishai, where they use this random walk idea to give a separation between BQP and PH. But the general idea here is that the higher moments of a multivariate Gaussian are controlled by its variances and covariances. And you can construct an MVG that has these nice covariances and variances using very few truly samples from a Gaussian independent. And you use balanced constructions of good balanced codes to do this dimension reduction, and then you discretize this whole construction. This is very high level and hand wavy, but that's as much as I'm going to talk about this construction.
Maybe something that's interesting is that epsilon biased are also entering the picture, but in a different way for constructing these balance codes. So
that's very true. Yeah, so our best constructions of these balance codes are the optimum constructions we know for epsilon biased distributions, and they somehow come into this picture again, but now in the construction of how to low dimensionally sample this MVG. Very good point. Okay, but this is interesting because if you want to break the log barrier for polynomials, this new result shows that all you need is to prove that the second level Fourier coefficient of an F2 polynomial are bounded by some polynomial in D. In fact, we conjecture that the bound should be D squared. So if you could prove this, then you get a PRG for F2 polynomials of degree log n, and you can read about importance of this other than just in terms of PRGs in a very good survey that Viola has written. But I have written this 1 over epsilon here in red because, so as compared to the original random walks idea that we had, we got poly log 1 over epsilon dependence in the seed length, but this construction gets only polynomial in 1 over epsilon. But we use a much weaker assumption. Instead of all levels, we only have second level Fourier coefficient bounds. And this fresh out of the oven, new work of Chattopadhyay et al. From pretty much last week, gives a hybrid in between these two worlds. Right? So they actually answer the question that can we construct an FPRG from some level K by showing that if you had a bound on the level K Fourier coefficients, L1 bound on the level K, then you can get better error dependence. So the larger the K, the better this dependence of seed length on epsilon becomes. So it's very interesting. And to make it more interesting, they show how to construct these PRGs using a weaker assumption than an L1 bound. So in particular, instead of taking the sum of the absolute values of the Fourier coefficients, so we define mk to be the maximum of just writing the sum of the expansion of the function at level k and then taking the absolute value. Okay. This is potentially much easier to prove bounds for because you can have all sorts of cancellations happening before you take the absolute value. So this is obviously mk of f is bounded by L1k of f, but this could potentially be much smaller. And what this new paper shows is that if there's some k, so this k has to be at least 3, and if you can prove that mk of f is at most b to the k, then you can construct a fractional PRG of seed length k log n. And this will be a p noticeable fractional PRG where p is epsilon to the 2 over kb squared. So you can see that it's better, and you can get a better PRG out of this by plugging it into the polarizing random walks. And in fact, they show that you can improve the seed length of this fractional PRG to log n plus log k over epsilon. If you had a bound on the L1 norm, but on the lower levels. So we still are not assuming a bound on all levels. We're saying that all of the tail bounds we have are up to level k. And on level k, we only have this without the absolute value bound. So it's very interesting. And combining it with the random walks construction, it gives you a PRG with seed length 1 over epsilon. So the dependence on epsilon will be something like 1 over epsilon to the 2 over k minus 2. So if you take k to be really large, the dependence is really small on epsilon. Okay. And obviously, it's going to be great to hear. It's a new work, and I'm excited to hear the authors to present it. But I thought that I would spend a little bit of time and present what I understood out of this proof. So it's a warm up, preparing you for the actual talk that they will give. So that, as you could already see, probably from the seed length, this is already telling what the generator is going to look like. We started to talk by mentioning a simple generator that has this seed length, which is k-wise independence. And the good news is that the construction is going to be basically multiplying a k-wise independent distribution by some value a, right? So very similar to the previous constructions that we discussed in this time. So we will discuss what this parameter a should be later in the calculations. Okay. So our goal is to show that this pseudorandom distribution, random variable x, fools any function f in the family. And we want to use this bound that we have, but we only have it for some level k. Well, we have this k minus 1 wise independence, and that suggests that we should sort of treat the Fourier coefficient based on their size being less than k or greater than or equal to k, because things that are less than k will just vanish when you have a k minus 1 wise independent distribution over a minus a to the n. The bias of all of these things are going to be 0. And all we are left to do is to try to bound this second term, which is the expectation of the tail, the above k tail of the Fourier expansion of f applied to this random variable x. Okay, so that's our goal now. So this is the only error term of this generator. And the key claim is that you can actually bound this by the following quantity. It's a over 1 minus a to the k times m sub k of the family f. And this is quite interesting because on the left, we have a quantity that's all of the levels above k appear. But on the right, we have a bound that involves only level k Fourier coefficients of f. And clearly, this is not true if I wrote lowercase f inside here. So the whole idea is to try to use the fact that the family f is closed under restrictions, and we have a bound on all the restrictions or variations of f. Okay, and if we could prove this claim, then you can see that if you pick a to be something like epsilon to the 1 over k over b, then this will allow us to bound this term, which was our error term, by epsilon. Good. So how do we prove this claim? So the idea is that to make this the following key definition, we will define a single variate real function g of t, where g of t is just equal to f of t times x. So let's assume that x is a vector that's fixed, and we define g of t to be f of t times x. And the trick is going to be to take derivatives of this function g. Okay. So there's two important observations. So the first one is, if I take the kth derivative of g, you can think of the definition. So you can look at the Fourier expansion of f at tx. So all of the monomials of degree less than k will disappear because they have a t to the some power less than k by them, right? Because we have t times x. And if you evaluate it at 0, so whatever terms you get from the Fourier coefficients that are of higher level, they will also vanish because they will have a surviving variable t in them. Right? So you had some t to the k plus 1 and you took k derivatives, t still survives. So when you plug in 0, they also vanish. So the kth derivative of g evaluated as 0 is exactly k factorials times the kth level Fourier expansion of f evaluated at x. Okay, so this is one important observation. And the main technical observation in this new paper is to use a Taylor's theorem approximation. And so we will write the Taylor expansion on g of 1. So what we want to evaluate what g of 1 is in terms of its derivatives. And why do we care about g of 1? Because g of 1 is exactly f of x. So that's the function that we care about. And the Taylor theorem tells us that g of 1, which is f of x, is the sum over all of the ith derivatives up to level k minus 1, evaluated at 0 divided by I factorial, plus an error term. And the error term is the kth derivative of g evaluated at some s. We don't know what s is, but we know that it's something between 0 and 1. Right? But what's cool here is that by the first observation, all of these terms are exactly the Fourier expansion of f up to level k minus 1. So we know that on the left, we have f of x. On the right, we have all of the up to level k. So this term must be all of the large tail of f, Fourier expansion of f. So even though we don't know what s is, we know that the kth derivative of g evaluated at s divided by k factorial is exactly this quantity, the expectation of which we want to bound. Remember, so we want to bound the expected value of this quantity exactly. And okay, so this part will be a little bit hand wavy, but so let's do it. So I will define a new function h of t, which is essentially f of s times x plus t times 1 minus a times x. And think of this way. So s is this point that's coming from the approximation. And I'm making sure that this vector still stays inside of the solid cube, right? Because x is taking values in a minus a, so I'm making sure that I don't step outside. And the idea will be that if you take the kth derivative of this new function h and evaluate it at 0, by the chain rule, you get basically 1 minus a to the number of times you took the derivative, which is 1 minus a to the k. and you plug in 0, so that the t part vanishes, so you get just kth derivative at s. Okay, so this is now becoming related to this quantity that we cared about. And finally, the final key observation is that because of the way H is defined, you can think of it as some convex combination of functions in the family, so restrictions of f. Because of the way this is defined, you can do this random variable trick again and write H as a convex hull of f, the family f. And what this allows us to do is to use this to this kth level bound, because we know that HK is this GK of S. So we know that we can use this kth level bounds on MK, and we have this a to the k. So for each functions that appear in the convex hull, we apply this MK bound. And we also have this normalizing parameter a to the k, because it's coming from the kth level Fourier coefficients all have this a to the k normalizing factor coming out of it, because x was a minus a to the n variable. And that's how you can bound this kth derivative evaluated at 0 by a quantity that's now related to MK. It wasn't clear, but I'm just trying to give some sort of intuition. And this allows us to bound GK of S. You combine these two, you get a bound on GK of S being bounded by exactly a over 1 minus a to the k. And we get this f, the quantity that we wanted to bound in the expectation is just that divided by k factorial. So that proves the claim that we wanted to prove. So it's a very elegant and nice idea. I recommend you to look up this new paper. It's available on arXiv. At least I think that maybe the ECC is not updated. In summary, what we did during this talk was we defined a new object called a fractional PRG, which was just simply a random variable that takes values inside of the Boolean cube, a solid Boolean cube. We showed how to use it to construct a PRG. And we showed that we can construct these fractional PRGs from assumptions on Fourier tails of the Boolean function family that we have at hand. And these were quite good fractional PRGs. I would give them maybe 3 stars. They're not as good as you wanted. They're not like log n over epsilon. They're pretty good. And later we showed that if you had only level 2 bounds, you get pretty decent FPRGs. Maybe if you care about epsilon, not very good. And this new paper shows that if you had kth level bounds for some large k, then you can get much better dependence. Maybe not logarithmic, but the larger the k, the better. And let me end by mentioning some open problems. So obviously, one of the problems that I care about is going to be to prove this bound on the second level Fourier coefficients and L1 bounds, which would give you a PRG for F2 polynomials. And in fact, it would give us the first non-trivial PRGs for AC0 with parity. It would give us polylogarithmic seed length for AC0 with parity if you combine it with Razumov-Smolensky type approximation by low degree polynomials. And motivated by this new work of Chattopadhyay et al., they conjecture that you can bound the kth level of F2 polynomials by some, if you can bound it by some quantity that's 2 to the little o of d, then even if you do this for k equal to 3, then you do break the log n barrier. You don't get polylogarithmic seed length, but you do get a non-trivial PRG for degree log n F2 polynomials. And I want to mention also that because this new PRG doesn't require a bound on all levels, even the current bounds that we had proved on the tail tail of the degree D polynomials suffice to plug it into this construction and get a PRG that's comparable to Viola's construction. So it is something interesting. It's a new PRG for F2 polynomials. And another interesting fact about trying to bound MK instead of the L1 bound of the Fourier coefficients is that this is provably related to proving correlation bounds with XOR of several copies of majority. So we already know that F2 polynomials have correlation roughly D over root n with one copy of majority. And if you could prove an XOR lemma for this kind of correlation bound, then you would get a bound for MK of F. And in a recent paper, we had some method of proving these kind of bounds, correlation bounds for majority, like XOR lemmas for majority. But the numerator, so we show that we do get this root n to the k, but somehow the numerator is not good enough for getting the correlation bounds that are good enough for PRG. So one open problem is to maybe try to see that if the techniques we had in this paper can be improved to get these better bounds on the MK of F. And that's all I had. Please ask if you have any questions.
Thank you.
Thank you. Any questions? That's a good point. So Shachar is pointing out that even bounds on M2 are open for polynomials. So we currently have some bounds, but they're not, they have really bad dependence on the degree. So, and another nice open problem is if you could come up with a PRG using M2. As I mentioned, that this new paper uses bounds on MK, but K has to be at least 3. So somehow we have a PRG if you use L1 bounds at level 2. We have a PRG if you have this MK bounds for levels above 3. And we don't even know how to prove good M2 bounds, which would still not necessarily, we don't know if it would give a PRG. It's a very good point. And in fact, I think if you can prove this, something like T over root n to the K correlation bound, then you get, oh, wait. Okay, so Shachar has another point that, so we don't know if it's true or not, but it is possible that we could make the CHAT paper, which is the one that's based on the Ras-Tal work, to make it work from M2. So that's another direction to consider. So currently we use absolute values, but we don't know if it would also go through from just without the absolute value bounds. So plenty of directions, and of course, so we have so far mostly focused on F2 polynomials, but if you find other applications, it would be very exciting.
Is there an approach that unifies these constructions to also get you PRGs for half spaces or LTFs? Like, I get this approach intuitively, it seems like it's related to L1 norm of the Fourier. it's related to epsilon bias spaces and L1 norms of Fourier coefficients, which I guess not true for majority.
It wouldn't, yeah, it wouldn't be suitable.
And is there some approach which unifies the two? Or like what is the construction? The construction of PRGs for NTFs. One is k-wise independent, but is there also something based on random restrictions?
So you can show some sort of simplifications under random restrictions, but I don't think that they're strong enough for using it in this framework. So like this, the probability of the restriction, the simplification happening is rather, but not happening is rather large. So it won't be strong enough for proving this kind of. But it's a very good question. So is there some sort of way to combine these two goals?
I mean, there's a different kind of fractional PRG for LTFs and polynomial threshold functions. So they're easier to fool in the Gaussian space.
That is correct, right? So there is we have better seed length generators known for things like polytopes if you care about only this kind of Gaussian generators and so on. That's correct.
Right.
Thanks.
But we don't know how to use them to get Boolean generators.
Exactly. So the current constructions for Booleans, like the best ones, still use invariance principles and such. Any other questions, comments?
So this at some point defined FP of X that looked exactly like the T-row operator applied to. It's exactly that, right? It's T-row operator applied there.
Yes, that's true. So in fact, so in some other works, when you have a bound on the Fourier tail, so one thing to do is to do this p-random restriction, and the expansion in the expectation will just have this p to the size of s coming out, and that's sort of what people would exploit in showing that with high probability you have simplification of some sort, so L1 bounds. So for example, the pseudorandom generators for bounded with branching programs in the unordered case uses these arguments, but we had to somehow argue the larger Fourier coefficient bounds by looking at the properties of the branching program and say that if the lower levels drop, then the higher levels also drop and things like that. But this sort of allows de-randomizing it by just doing the expectation and giving FPRG, if that made any sense, this explanation. But sort of, yeah, so previously these things would come up, but then you had to sort of de-randomize it and look at the family to see simplification happens.
Any other questions? Okay. Yeah, if there are no other questions, let's thank Pooya. Wonderful talk.
Thank you.
Yeah, thanks everyone for coming to the talks. This was all the talks we had planned for the series. Really, I mean, we want to continue the series, but also there are a lot of programs starting at Simon's right now. But we are debating whether to continue the series or not. There's clearly a lot of works, exciting things happening in this area. Yeah. So we'll keep you posted. If you do plan to continue with it, send to the, we'll email once more to the same mailing list that we had. Yeah. Thanks everyone for coming to the series. Thank you.
Yeah, thanks again for organizing this lecture series.
Thank you, Pooya.